So for tonight's presentation, we got our own Professor Comet, Justin McCollum, who's been a long time FBAC member, also has degrees from Portland State University in UT and physics, and is also certified in artificial intelligence. He is involved in physics laboratory and astronomy, space and sciences, and instructs at Lamar University. And so his interests are photometry and morphological studies, behaviors, Professor Comet. And for tonight's presentation, Justin will be talking about globular clusters, which are awesome visual objects to look at, and also for photography as well. So welcome, Justin. Love to start the talk.
So this is exploring the nature and weirdness of globular clusters. I gave this presentation, very similar one. This was with the North Houston Astronomy Club about a year ago. So we should all be familiar with globular clusters. These are large islands or concentrations of stars. They're very old. They're strongly bound together by their mutual field of gravity. They were all formed as sort of separate islands of dust and gas that broke out of the original protogalactic clouds, because these globular clusters tend to form around the galaxies, whether they are elliptical or spiral galaxies. Very low concentrations of metals, since they tend to be the first generations of stars. They're poorly understood. There's a lot about globular clusters we don't understand. They could be pinnacles for learning more about galactic evolution. And this is looking at deep into one of the, well, there's another globular cluster. Here's another globular cluster. I think this is part of Bates' window through Sagittarius, that gap in the spiral arms. And there are multiple populations that exist within these globular clusters. And the groupings of stars match that with the galactic bulges of spiral arms in terms of the age and chemistry, as well as that of elliptical galaxies. Now, the first thing we know about is that Johann Abraham L.A., which was a German astronomer who around in 1665 actually made the observations, the first observations of coming across this object. And this was actually the oldest objects of all of the 110 objects in the Messier catalog. Unfortunately, we have no original portraits or any of his recording observations. They are referred to secondary in Charles Messier's recordings. But here we have from William Herschel's publications, so we can see that sort of dots right there, always going towards the center. So even in the earliest uses of telescopes, we could see sort of the structure beyond the fuzzball, the distinguishing of the stars spreading out versus being very condensed. These are all the people that contributed, both from the Middle East and from Aristotle, and many of the big astronomers that were famous at that time in the early ages of astronomy, mostly from the 17th and 18th century. Charles Messier, of course, discovered 13 comets of his own. He was the big comet hunter, because comets was the thing back in astronomy before there was such a thing as globular clusters in galaxies. But his catalog was not entirely 110 objects. We have about 1, 2, 3, 4, 5, about 7 objects that were added on from 1921 to 1967 as reevaluating many of the old archives around the time of Messier in the 18th century. This is more akin, this left image is more akin to what would have been seen in a lot of the refractor telescopes at that time period. This is a more modern image. Here we come from documentation, not only from Charles Messier, but also from William Herschel in terms of what they would actually see in their telescopes. And here's the actual writing up from his document here, from his publications. And this was in 1781. And that's the reference to Messier 15, is referring to this sort of condensed ball of stars that slightly became more and more compressed towards the center. William Herschel, we have his 7,500 non-stellar fuzzies from his publications. And this was one of his telescopes. And the speculum mirror is no different from that used by the Romans, 2/3 copper, 1/3 tin. It would not be until over a century later that astronomers would learn and opticians learn how to shape glass into mirrors. And here we have his recording of his images. You can see how some of these look like galaxies and planetary nebulas and open star clusters and globulars. This is his big 40-foot telescope he used to scan across the sky. His peak of observing was between 1783 and 1790. It was the largest in the world for 50 years. He would stare down into the tube with a little refractor to stare down and look into that big mirror, and attributed a lot of discoveries of globular clusters due to this telescope. 2 mirrors were made, duplicate mirrors, each of them with an f10 focal ratio. This was from his son, John Herschel, one of the earliest photographs from 1839. The A-frame structure was still attached. There is that raising platform right there. There is the housing, but the tube has long since gone, but the 2 mirrors were still intact. Now, one of the things was how the globular clusters played a role in understanding the universe outside the Milky Way galaxy. There was a great debate. This was known as the Great Debate of 1920 at the Smithsonian Museum of Natural History. Here we have Harlow Shapley and Heber Curtis, one of the great early astronomers in terms of bringing into the modern astronomy, modern cosmology, going from the late 19th and the early 20th century. And there was great debates about the nature of the galaxy itself and how we determine the brightness of stars, the types of stars, distances. Both men were right and wrong about 2 particular things. Well, Shapley was right about the size and structure of the Milky Way galaxy, but he thought it was the only thing that existed in the whole universe. Whereas Curtis was right about the idea that there were other galaxies, other island universes. So we would refer to those originally as the spiral nebulae. You have the island universes, and then the term galaxies didn't come into use until the 1920s. But he was wrong about the size and structure of the Milky Way. And it all comes to where we map out the globular clusters. So this was William Herschel's map. This was a map of Cornelius Epstein around 1900. So you can see where we have the positions of the constellations, the heliocentric model of the Milky Way, and here's the bulk of the galaxy. Right down here is Arthur Eddington's image from 1912, but Shapley's map right here, he had it correct because the X represented the center of the galaxy. You can see where he mapped out the globular clusters, and that's pretty accurate to today. And you can see where he has our solar system not at the center of the Milky Way galaxy, but far from it, where the globular clusters sort of gather around, which is the central bulge of the Milky Way galaxy. Now, we have about over 200 that were known. About 169 of them have established common names. The Camargo catalog from Italy was a big project that was using many of the big Ys and the 2-mass telescope surveys. This actually looked across the inner part of the Milky Way, of which there are about 1,100 objects or targets as candidates for galactic star clusters, sort of a grander version of an open star cluster, as well as globular cluster candidates, of which 5 have been added to our list of known Milky Way galaxies. And I have them here, the 1105, 1106, 1104, 1103, 1102. You cannot actually see these because you have to pierce deep into the heart of the Milky Way galaxies. These are all viewed from infrared surveys. One thing is that we find about globular clusters is that they only have the fractions of the metals that we see with the sun. 10%, 1%, 0.1%. This is a stream of stars known as the C19. The metallicity, basically the amount of metals, is basically less than 1/10 of 1%, even less than 1/20th of 1%. And that's the one thing, is that these globular clusters have a very low metal concentration. The size range is very wide, between a few dozen to up to about 1 million light years across. Actually, I should probably backtrack on that. I think I meant to say about 1,000 light years. Well, the size range is actually from a few dozen to upwards about, I should say, about 1 million stars in terms of the mass. So that will probably have to be corrected. But the size is between 10 to 110, 20 to 110 light years in size. So I meant to say this in terms of about a few dozen up to probably about the size range. I meant for that to be sort of like the mass in terms of the amount of stars. I meant to say a few 100,000 upwards to about 1 million. But what's important is that all the globular clusters are about 100,000 stars at least. Some will contain upwards between 100,000 to 500,000 stars. And I probably meant for that to be up to about over 1 million stars, but in that case, they tend to be globular. The globular clusters can be cataloged as dwarf galaxy remnants. They're very old, but the age range can be wide between 8 to 12.7 billion. Very few are 13 billion years old. We have about 200 candidates to 169 with no names, although the number is probably going to increase more to several hundred. There are galaxies like the big elliptical galaxies that can have upwards of 10,000, even 15,000 globulars. Now we have to remember there's what we call the half-life light radius versus that of the tidal radius, because you can have a globular cluster that is 20 light years in size due to the concentration of the stars, but then the effects gravitationally can be about 10 times that. So 200 known globulars, of which we have 169 that we've established with names other than the catalog designations. Let me go back there. I was using the wrong button. One thing is that they all fit within the population 2 stars, meaning they're very low metals, like we see at the elliptical galaxies and at the central bulges. So that places a lot of them forming in this time range here, where this is 13.7 billion years in the past versus out of the present day. The density can vary, but usually you can get it up to anywhere from 0.4 to about 1,000 stars per cubic parsec. So imagine instead of the nearest star to us being 4.25 light years away, it's only about 1/10 of a light year away. Very intense radiation environments. This is the Shapley-Sawyer classification system. It goes from, this is where we have almost no concentration, I'd say almost no concentration towards the center, versus that of the highest amount of concentration as you go from left to right and going down. So we have a very concentrated pack of stars at 1, and then right here, this is one of the polymers where the stars are very distributed outwards, and that should actually say almost no concentration towards the center. So we can classify these globular clusters based on the nature of the concentration of the stars in the central region versus the outer areas where they're more dispersed. There is what we call the Osterhoff groups, where basically we're dealing with metal rich and metal poor. I know these globular clusters are very metal poor, but the difference between being 1% or between 10% to 1% versus 1% to less than 1/10 of 1% of the amount of metals compared to the sun. This is Tarzan 7. It's the type 1, so it's metal rich. The type 2s, like this one here in ARA, ESO 280-SCO6, that's metal poor. And where we find metal poor globular clusters, we see the high concentration of the RR Lyrae variable stars. Some of them can also be remnants of dwarf galaxies, where we get the intense gravitational force from the parent galaxy that literally tears off a lot of the stars from these dwarf galaxies, reducing them to almost like a globular cluster-like structure. There's also, all globulars face a certain amount of evaporation rate, the loss of stars as they trail either ahead or behind the globular cluster. Because every time a globular cluster passes through a galaxy, particularly a spiral galaxy, the stellar associations and the huge amounts of dust in the spiral arms can actually tear apart stars from the outer edge of the globular cluster. So the globular clusters are basically receding in their structure. And a few of them are massive enough that we've actually confirmed now the existence of many intermediate massive black holes. That is on the scale of hundreds of thousands of times the mass of the sun. Not like the big galactic, well, the big supermassive black holes. They're on the scale of millions to billions of times the mass of the sun. So most globular clusters reside within a galactic halo. So here's the halo. It would be the same thing for an elliptical galaxy. The only difference is being that the elliptical galaxy, just think of this as just being just the bulge itself without the spiral arms. And yes, we do get the globular clusters passing through the spiral arms, and some of them can get destroyed and become stellar streams. That is, they're simply just torn asunder. They're very close inside the galactic bulge because the mass of all these stars with a combined gravity can overwhelm any globular cluster. But we find a lot of the concentration within 8 to 10 kiloparsecs. That is within just a fraction, some cases only about maybe 1/3 to 1/5 of the length or the diameter of, or the radius of these, any type of galaxy. One thing is highly elliptical orbits. Basically, a globular cluster can stretch out to about a few 100,000 light years from the center of the galaxy. And then when they come to the other end of the orbit, it's like maybe only like 20 or 30,000 light years away. So we get highly elliptical orbits. The speeds average between 400 to 500 kilometers per second, and they will vary substantially. And a lot of these globular clusters over time, their axial tilt will change, their eccentricity will change. So the orbits undergo, and also there will be sort of a very galactic precession where they will sort of wobble around the center of the galaxy itself. Here is a deep inside view, and we can find that as we go deep inside, like with this globular cluster, NGC 6397, we can locate white dwarfs. There are actually cases where you have some of the first stars being supergiant stars inside the globular clusters. They blow apart, they create short-living giant stars, and those giant stars are just at the right mass where they leave behind clusters of white dwarfs residing inside the globular cluster. So these are all individual white dwarfs that have been photographed piercing deep into these globular clusters. The red giant branch, what's very, very important is that the lower end is right at the F-class stars. You don't find any of the O, B, or A class. You don't find any of the big blue giants or blue supergiant stars. They tend to, what happens is that there tends to be the short cutoff rate, which we find with all star clusters, where the stars will reach a certain spectral layer, a certain spectral classification, then they cut off into the horizontal red branch, and then they get into these very aged large stars. Any recent formation in the globular clusters beyond the initial formation at the beginning of the galaxy will usually occur as they're passing through the spiral arms, because you get all that formation that happens within the first 2 billion years of a galaxy, and then there's no more star formation with those globular clusters after the first 2 billion years. Anything that occurs is when these globular clusters are passing through the galaxy, and it's usually the interactions of these giant molecular clouds and the big stellar associations that have hundreds of millions of stars. Then they'll start tugging around the stars in the center of the globular cluster, and then you get white dwarfs colliding together, and then they form these blue stragglers, these bright bluish stars. But they are a small minority of those stars. They tend to reside deep within the center of the globular clusters. So here we have the possible helium white dwarfs, the blue stragglers, they're right there. So they do exist. This is looking deep with the Hubble inside Toucan 47. If you have to see any James Webb images deep within the globular clusters. This here talks about the mass segregation, and really it's a matter of what type of theory is going to be proven to provide the best evidence for the nature of the evolution of globular clusters in terms of the stars. But what you would get is that in the two scenarios, you would get the first generations of stars, and some of them would be the supergiants, and then they would undergo basically a nova effect, and then create a second generation of younger stars that have slightly more metal than the older generations of stars. But they would be distinguished between the Ostrov type 1s versus the Ostrov type 2s. We do get formation of T-Tauri stars. We do get the OB stars themselves that form inside here, and then they blow off to create sort of these superclusters of the much younger, hotter stars that don't last, and then they create the second generations of the lower mass stars. So you do get at least 2 generations of stars that form inside the globular clusters, and you tend to have them inside. The first generation tends to be outside here, and then you get your second generation. This is mostly for the F and G class stars. Then we have the supergiants. What's more interesting is that these stars here tend to have a higher metal than these other types of stars. And what we see here is that it fits with about a 2 billion year time period in which the globular clusters in the first 2 billion years are going to be forming these stars. How they form depends really on the nature of the galaxy itself. We talked about how there's a bunch of mass in a globular, in a protogalactic cloud. If it's spinning very fast, doesn't have a lot of mass, it's going to form a spiral galaxy. If it's spinning very slowly, but it collapses pretty quickly, it becomes an elliptical galaxy, and that affects where we're going to see the motional behavior of the globular clusters. This is very interesting because we can look how we have the much hotter stars, the bluer stars towards here in the uplift and the downlift bends in this case here with the Milky Way galaxy, and then we get into the redder stars as we head towards the population 2 stars right here in the galactic bulge. But you have to realize that we can get the F2 and F6. So these are the much more hotter, whiter stars with the globular clusters in the outer region of the halo. We get into the mid-halo region, and we get into the much cooler F-class stars. And then we get into more sun-like stars in the G0 and G5 classification for the globular clusters in the inner region. So the globular clusters, as we go from those that naturally exist in the edge of the halo towards the central region of the halo, they tend to become a bit more reddish. I won't double on this a bit, but one of the most interesting things is that when we think of the turnoff points, it can vary wildly for open star clusters. So open star clusters can have anywhere from M to an O class stars, from the very red to the very bluish. Whereas with all globular clusters, they have the similar turnoff rate, and the turnoff rate is very short. They can go up to the hot end of the F-class stars, and that's it. Unless they have blue stragglers forming, no O, A, and B class stars whatsoever. In fact, they tend to have very few supergiant stars that still exist. And this is just an overlap. We have to remember the globular star clusters are going to have tens of thousands to hundreds of thousands of stars, up to over 1 million stars. A lot of bright red giant stars. They're very old. They're no longer forming any new stars. They're very poor in metals, opposite from that of the open star clusters. But they do tend to have stars that are close together, of sort of the similar distances from the sun. The star colors do indicate the age of the globular clusters. They do orbit around the center of the Milky Way galaxy, and they are bound together by mutual gravitational attraction. But open star clusters, it's very weak. The globulars are pretty strong in terms of their gravitational attraction. One thing is looking at the marker to determine the distance and ages of globular clusters are the RR Lyrae variable stars, for those globular clusters that are very low in the metallicity, that is the amount of metals. And with the RR Lyrae stars, you've got few hours to 1 day for the periodic motion. That is the change in brightness, which is from 0.3 to 2 magnitudes. Here we can actually see some of these RR Lyrae stars in M3, and I just picked out 1, 2, 3, 4, 5, 6, 7. There's dozens of more in here. And when you get a globular cluster that has these variable stars, they're going to have a lot of variable stars, hundreds of them. This right here, if you look at over here where the stars are flickering a bit, right here, this is what we use a logarithmically scaled image. That is, we can enhance the coloring between the red and the blue to see the difference in magnitude. And that can be used to catalog the stars here, particularly right here with this. I forgot what globular clusters this was, but this allows us to better map out three-dimensionally the size of the globular cluster and the distances of the stars. Right here, we can use that same logarithmically scaled version. I think this was for M3, and you can see the stars flickering right there. And that allows us to really pick out the variable stars and look at the brightness and change in brightness. And we can measure the depth, the shape, the structure, and the distance of the globular clusters. And this was taken from the Moore Observatory, courtesy of Joel Hartman, Princeton University. He used a CDK, but a 20-inch scope. So something you can use with CDK scopes. Those are the Cassegrain-Dahl Kirkhams. And you can see, everybody see the blinking period right there? The difference with the RR Lyrae versus the Cepheid variables. They tend to blink at different rates. So I think that's a Cepheid variable, and there are the RR Lyrae stars. I picked out about maybe like 30 of them blinking in that scope. I mean, blinking in this globular cluster. This is M5. So here we look at the differences in the range of brightness and variation between the different types of Cepheids and that of the RR Lyrae stars as different means of determining the distance, shape, and structure of these globular clusters. And how they move around the globular cluster can lead to a bit of a redshifting of that light, which can affect the variable pattern. This is variable star V1. I put that in there so you can see how we can also look at the nature of globular clusters in other galaxies. The V1 is a star by itself that orbits the Milky Way galaxy. Difference here is in the concentration of brightness between the type 1 and the type 2s. The type 1 are classical, the type 2s are up to the W Virginis star. We can also sort of map out the patterns of the stars here. And it's very important that we look at the period luminosity, what we call the distance modulus. Because when we're mapping out the stars in these globular clusters, the same way we map out the nature of measuring distances to galaxies and determine the shape of galaxies, we can correlate that with the shape, the structure, and the motion of globular clusters. That actually appeared differently, but this is the range of magnitudes. This is the periodicity. Here we located in Messier 5. So this is the map of Messier 5 from the AAVSO. One of the errors here in the blinking images is that right there is V84. No, I'm sorry, that's V42. It's not blinking, whereas V84 is blinking. That shows you the difference between the Cepheid and the RV Tauri. But remember, all these stars are, well, at least with the Tauri stars, they're in this instability strip, which is a temporary state. As they move out of the main sequence to the horizontal red giant branches, they're moving into the red giant stars, approaching the end of their lives. And the periodicity motion is very important because it allows us to determine the overall brightness of the globular cluster. And we can actually get some inference into that as the mass of the globular clusters. So you can see how it abruptly turns. We don't have in the OBA stars right here. We can see that abrupt turn right here with Messier 5, that abrupt short turn. And we see most of these stars moving into the giant phase, but none into the supergiant or hypergiant phase for the stars. And looking at the different methods for brightness of the stars, this is for distances, is distance modulus. And there's actually an equation that we use for that. And I thought I had shown it here, but it appears to be missing. But there's an overall formula that we can measure based on looking at the distance, based on the brightness that we see versus the actual brightness. If these things were 10 parsecs away, measure the distance in parsecs. So we can use that difference in brightness to measure the distances of these globular clusters. Oh, I'm going the wrong way. One thing is that the orbital period of these globular clusters, we can look at the motion of these stars, looking at the spectra, looking at the regressional and relational velocities. And we can see how this is what we call the galactocentric. So we can look at the structure of these orbits, their radial distances from the center of the Milky Way. We can look at this sort of along the plane of the Milky Way galaxy and see how the orbits are actually changing. Every time a globular cluster orbits once around the Milky Way galaxy or around any galaxy, the orbit will change, the eccentricity, the shape of it will change, the periodic motion will change, and its tilt will change. But that occurs in some cases anywhere from 300 to 800 million years. And we can also see the precessional motion. This is along the meridial plane, which is perpendicular to the plane of the Milky Way galaxy. So the globular clusters their orbits can sort of precess around the center of the Milky Way galaxy. And that can occur anywhere from 400 million to about 8 to 10 billion years.
Justin, question.
Yeah.
Okay, we've been looking at the globular clusters for a couple hundred years.
Mm-hmm.
How have we been able to determine these orbital characteristics?
Well, this is a projection based on looking at the spectra of these stars and looking at the photometry of the stars, the brightness, and seeing how they're actually moving. And we can extrapolate that. And the globular clusters are in a tight pattern, so they all sort of move at the same speed. Right here, we can look at how the orbital velocities actually change. Globular, we have to remember that as the stars are spread out around a globular cluster, there will be a huge change in the orbital velocities. But as the globular clusters are pretty tight with terms of the stars are all going to sort of move around at sort of the same speed. So the further the stars are from the barycenter, the lower their orbital velocities will be. But there will also be a narrow range in the orbital velocities as these stars are tight around the globular clusters. So we can use them as a good means of extrapolating what are going to be the changes in the orbits of these globular clusters, and they can provide insight into the behavior of the galaxies. Now we have our regions. We have mostly white dwarfs at the center, and we mostly have main sequence stars here in the middle region, and then it's more of a variety in the more dispersed area right here. So we can break up the globular clusters into three regions: the white dwarf region, then there is the main sequence middle region, and there's the more dispersed outer area. What's interesting is that we get higher orbital velocities about the globular cluster's barycenter right here. And then the velocities are a lot lower. That is, they're orbiting a lot less with the more of the main sequence stars out at the edge. So the higher velocities are going to be for the very old white dwarfs here, and then for the very old main sequence stars that are not quite as old, they're going to have the lower velocities out at the edge. One thing is that we get very little dispersion of the stars here in the center. There are fewer stars with greater dispersion, but a lot of the evaporation rate in terms of the star loss for these galaxies are occurring along the outer edge right here. And some of these stars will actually make their way out, and then over time, this more concentrated central area will begin to spread out. So the globular clusters will dissipate over trillions of years. Now, right here, we can see it brighter in the center with the white dwarfs. We have the less massive stars with greater luminosity. But in terms of the light output for the stars themselves, we find that there is going to be a much greater light output here from the center. But the white dwarfs are not going to be very, very bright, but it doesn't matter. There's a lot of them, whereas the main sequence stars are going to have a lot of light output, but because there's so few of them, it's not going to look very, very bright. And so we may have the very massive stars out here that have a huge surface area that produce a lot of light, but because they're so dispersed outwards, we get into much larger stars, less with the white dwarfs. They can produce greater light for each individual star, but since they're more dispersed out, the luminosity becomes less and less. This looking at the changes in the polarization of light based on the red shifting, and it's three-dimensional. So not only we can determine how the globular cluster spins about its own axes, but whereas it's moving through the galaxy itself, through the galactic halo, whether they're moving towards or away. And the difference between the faster speeds and the slower speeds, the more the globular clusters are going to flatten out. So we have most globular clusters spinning about their axes at around 3 to 8 kilometers per second. That's just how the stars are spinning around. As we get towards the central 10 kiloparsecs, the speeds get about better, about 50 to 80 kilometers per second. And as we get into the inner region where we have the white dwarfs, the speed is a lot higher, between 100 and 120 kilometers per second. And they all move in prograde orbits. And globular clusters, of course, will have different speeds in different directions for those stars within the globular clusters as they're moving sort of further and further out. So there's also, this is for where we have the motion for the globular clusters themselves. They're out here, they can be very, very slow. And as they get closer towards closer towards the center of the Milky Way galaxy, they're actually going to be speeding up to this level of speed. There's no such thing as a retrograde globular cluster that orbits around a galaxy. I've never found one. This is the color magnitude diagram, so it deals with the effects of the generations of stars. One thing we can say about this is that the first generations of stars tend to have higher helium concentrations. The second generations actually collect metals that were the result of some of the larger stars that died out from the first generations. But any star formation would have been highly burst. There would have been a high burst of star formation. it would have been very, very rapid and very quick and a lot more efficient. But we look at the different populations of stars because we can look at the different amounts of calcium. Even though the calcium concentration is very low, it's very distinct between determining one generation from another generation, from the G1, from the 1G to the 2G generations of stars. One thing is the presence of pulsars. They have an effect on the magnetic field of the galaxy itself, because these pulsars create a very distinguishing magnetic field for the globular clusters, and they tend to move around the charged particles, which can create these sort of wakes within these globular clusters that can actually create a bit of turbulence within the magnetic field of the galaxy around the galactic halo. You get a lot of ionized gas that gets ejected out of these globular clusters because of these pulsars that are actually enhancing the magnetic field for these globular clusters, and that can contribute possibly to why the globular clusters don't really form any more stars. 47 Tucanae actually has 25 known pulsars. And these pulsars in the globular clusters actually contribute a lot to the turbulence within the magnetic field of the Milky Way galaxy, and it has an effect on the behavior and the nature of the halo stars within the galactic halo, particularly with our Milky Way galaxy. There is the line of sight. We can look at the flow of these globular clusters as they move through the galaxy's magnetic field, and they create a bow shock of their own. So when you have any object with a magnetic field that moves through an object with a larger magnetic field, it's going to create these bow shocks, and it tends to build up energy, builds up plasma. It acts as a radiation that works sometimes with or against the globular cluster with respect to the magnetic field. And so what we get here is that we get the winds in the galactic winds in the galactic halo. The magnetic field gets stronger because these galactic winds have charges that build up the strength of the magnetic fields. The globular clusters move at 45 kilometers per second just based on the gravitational influence. The winds exert a pressure of 200 kilometers per second. And so we get a perpendicular to the galaxy. We can get, for instance, in the case of 47 Tucanae, it can basically move it up to 245 kilometers per second. And it can actually change the rotational motion within the field of not only of the globular clusters, but it can also have an influence in the motion of the magnetic field lines within the galaxy itself. And all the globular clusters tend to contribute to that. Oh, black holes and stellar remnants. A less dense globular cluster, they can also have substantial populations of black holes at the core. There are some indications, like with Caldwell 79 and also with Mayall 2. Mayall 2 is believed to have possibly a 20,000 solar mass central black hole. That was one of the initial measurements, but there's also believed to be anywhere from up to 5 to 100 black hole, clusters of black holes containing anywhere from 5 to 100 members in some of these globular clusters that can be up to about 1,000 times the mass of the sun. But instead of it being one intermediate mass black hole, it's a black hole cluster. That's one thing we're now looking at is black hole clustering. Globular clusters existed very early in the universe. We find them in elliptical galaxies. We find them in a lot of the dwarf galaxies. There is a map from the old atlas of M31. Here's a chapter that we can pick out the globular clusters. M87, all these little dots right here, is each one of them is a globular cluster, actually comparable to Tucanae 47. So a lot of massive globular clusters. Is anybody familiar with the Sparkle galaxy from the James Webb images? These three images here are actually the same galaxy, but as they get bent around these more massive elliptical galaxies, it tends to alter and warp the shape as we see here. So this is 1, 2, and 3. Gravitational microlensing can be funny because if you look at these dots right here, these red dots, they are exactly, look at the spectra, they're the same object. So we're looking at the same galaxy. So there are 12 unresolved red spots. We see as it looked about 9 billion years ago. Formation was in the first 500 million years. The age of the clusters is 13 billion years old. That would put it at a distance of 13.69 gigalight years. But if we look at the co-moving distance, it's probably over 40 billion light years away. The presence of white dwarfs gives it an age of 12.5 billion years, but this is why we're looking at it in infrared, why we can't see invisible light, because look at the redshift, about 5 to 9. But one thing about the gravitational microlensing is that it enhances it and magnifies it by a factor of 10 to 100 times. Otherwise, this may be beyond the capabilities of the James Webb. But every one of those red spots are basically globular clusters. Now, strange features of certain globular clusters. Messier 15. We only know about a handful of globular clusters in which we found 4 planetary nebulas found. Has anybody ever looked at P1 in a telescope? I've seen it a few times. An O3 filter at about 600 power with an 18-inch mirror is best to see it. Francis C.G. Pease was actually an observer and an optician who worked at the Greenwich, not the Greenwich, but the Yerkes Observatory. There's a picture of him right there. This is in infrared. This is visible light. I actually have a map here where you can actually find it. There's the trapeze, which is right there. There's the A, B, and D star. C star, there's a triangle. The E star is right about up here, and then this little patch above it, that is where phase 1 is located. There's actually, in other circumstances, when you look up close towards the globular cluster, you can pick out these stars, you can locate phase 1. So you actually have asterisms to which you can locate that nebula and actually see it. This is Caldwell 80. It actually is a possible disrupted dwarf galaxy. It probably has a 8,200 solar mass black hole. They actually can look at the stars in the middle from decades of observations and project the motions of stars over a 600-year period. Capitan star, which is like less than 15 light years from Earth, likely came from this globular cluster. It's a class M1, a red subdwarf star, because its calcium concentration matches that with many of the earlier generations of stars, the 1G generation of stars within the globular cluster, Omega Centauri. So if you ever look at Capitan star, you realize you're looking at a possible member of Caldwell 80, of Omega Centauri. NGC 104, that's the famous 47 Toucan. Lots of exotic stars, blue stragglers, 35 millisecond pulsars, stars with chromospheric activity that rivals that of the sun during the peak of its solar cycle. Lots of these X-ray binaries with neutron stars, lots of cataclysmic variable stars. And even though it's 13 billion years old, there's still continuing mass segregation, which means there's still a separation of the 1G and the 2G stars, where the 2G stars would be out here and the 1G stars towards the center. And that's odd because we would expect globular clusters to have completely undergone complete mass segregation, the separation between the two generations of stars billions of years ago. This is Palomar 5. It's actually better when we don't have the lights shining. You can see more of the stars, but this has a stellar stream that's a lot larger than the globular cluster. It's about 5,000 solar masses of that globular cluster that's now in a stream 30,000 light years long. So it's literally being pulled apart. And it has an aspect ratio of 0.62 between the major and minor axes. So that means it's like an oblate spheroid. It's very flat at one end and it bulges really outward. So it's a very flattened class 12 globular cluster. I think in the elliptical galaxies, we'd be more like an E7 or an E8, really elliptical shape. So not all these globular clusters are going to have a nice ball structure. Palomar 12, it's actually 30% younger than most of the Milky Way globular clusters. Why? Because look at this right here, the iron to hydrogen ratio, it's negative 0.8. And what's a negative number? It means that we expect to find a lot more metals than hydrogen in these stars by looking at the spectral lines. So, and it's only 6.5 billion years old, because you can look at the average metallicity, that is the amount of, and it doesn't mean that it's iron so much as hydrogen, is that what are the types of metals compared to hydrogen? Iron is used as a marker. And when you have a lot more iron than hydrogen, it basically means you have later generations of stars, and this is a very young globular cluster. It's very young, it's very metal rich, it represents that extreme end of the Ostrov type 2s. This is Whiting 1. It has a metallicity of 1.2. It has very low metals, and it's only 5 gigayears in age. So that means it has almost no metals in the stars. They're mostly just balls of hydrogen and helium. And no, these are not going to be those population 3 stars. It's considered to be the youngest known globular cluster. It's not an open cluster, but it is a halo object and has all of the spectral features for stars and the behavior of the stars inside that we would expect for a globular cluster. But there is the dwarf spherical galaxy that's being pulled apart, known as Sagdag. Everybody ever read about Sagdag? It's this dwarf elliptical galaxy that's being pulled apart. It's a part of, almost part of the Milky Way galaxy as a satellite galaxy. This is a former member of it. So,
I'm sorry.
yeah.
How do you distinguish this as being globular instead of open?
Well, it's looking at the fact this only has 2 generations of stars, whereas most open star clusters will tend to have 2 or 3 or 4 generations of stars. And also the motion of the stars that circle around the center of mass. It's very indicative of a globular cluster. But as one thing about the Milky Way galaxy, it likes to hoard globular clusters. It basically swallows up and destroys and cannibalizes dwarf galaxies and literally steals them of their globular clusters. This is Messier 4. It's got, it has a higher content of lithium than what's expected for such an old object. One thing about globular clusters is that we expect very low amounts of lithium. It's got white dwarf stars that are nearly as old as the universe. It has a CX1, but basically what it is, the CX1, we've been able to confirm there's actually an exoplanet in a globular cluster. So you have an X-ray binary where you have a neutron star and a pulsar. They're orbiting around each other. Well, actually, this is a pulsar and a white dwarf. So you have a pulsar and a white dwarf. They're orbiting around each other. And then there's a big super Jupiter planet orbiting around them. So you get the white dwarf and the pulsar orbiting around each other. And then outside that orbit is basically a Jupiter-like planet that's 2.5 times the mass of Jupiter. And the orbital period between the 2 stars is 6.3 hours. So they're whipping around each other pretty fast. Here's another one. This is Mayo 2 Andromeda's cluster. A luminosity of 2 million suns. The tidal size, that's the one thing. This globular cluster is only 50 light years across. That's what we call the half-life diameter, which means this is where most of the stars can be located. But its gravitational influence can drag in stars up to 526 light years across. So basically, its tidal size is about 10 times that volume with respect to the volume of stars that occupy the globular cluster. And it has a wide range distribution of multiple star generations. Usually there's actually a 3rd generation of stars. So even though it may look like a globular cluster, it probably is a remnant dwarf galaxy. So it's somewhat been cannibalized by the Andromeda galaxy. And it's had a large stellar creation period, about 1 billion years longer than that for the 2 billion year period of globular clusters, not only in our galaxy, but we see in other galaxies. Caldwell 25, NGC 2419, another possible remnant dwarf spheroidal galaxy. Everybody should know this. It's the intergalactic wanderer that's sort of moving at 350,000 light years away. What's odd about it is that it came from another galaxy. It's moving through our galaxy and it's receiving a gravitational sort of slingshot by the Milky Way galaxy. So it's moving through the galactic halo, and it's not going to stay there. So it's going to be sort of that rogue dwarf galaxy remnant / gigantic globular cluster. If it's actually very close to us, it would probably be as bright as Omega Centauri. But it does have a stellar population that's unusually rich in helium.
So is it leaving us now, or?
It's moving through the galactic halo. It's sort of halfway between moving towards us and moving away from us. So yes, it's receiving a gravitational slingshot by the Milky Way galaxy.
It's about as close as it's ever going to get right now.
Yes, but it's passing by us. But if it was very close to us, it's very massive. It would probably be I think, as bright as Omega Centauri. But it's unusually weird globular cluster because it came from another galaxy. It didn't come from, in fact, it didn't even come from any of the galaxies in our local group. So it actually came from a different galactic cluster. So it's an intergalactic wanderer. It's been traveling through intergalactic space. Messier 71, no RR Lyrae stars, has no central compression of stars. It looks like an openly packed open star cluster, but if you see the short branch right here and no O, B, or A class stars, that is very characteristic of globular clusters. There's no wide spectral turnoff, and there's none of the stars becoming giants and supergiants. And the age is 9 to 10 billion years, which is unusual for open star clusters. This one right here, I'm sorry you can't see it, but there's a lot of blue stars in there. This is something I found in a document that was published back in 2005. I call it the Ursa Major blue cluster, but a lot of people think that this is either an unusual globular cluster or an extreme dwarf satellite. It actually has very few horizontal RBG stars like that of Artemis 4, which has also been classified as a globular cluster. The half-life radius, which means that most of the stars are going to be within an area of 23 parsecs, so 46 parsecs, so that's about 100, 120 light years, but that still fits with that of a globular cluster. It's an old metal poor star system, but it's an overdensity of resolved blue stars. So it's sort of that boundary object between the ultra faint, sort of those blue dwarf spherical galaxies, these blue galaxies we're finding, these faint little blue dwarfs, these hobbit galaxies, and that of globular clusters.
So what is a resolved blue star?
Well, in terms of being able to pick out the stars as being a point of light, whereas these unresolved stars, they can detect these stars. They can't seem to just not have enough resolution to pick it out, but they can detect the light and they can look at the spectra and see, oh, it's a blue star. And from the spectra, they get that Boltzmann maximum to look at the surface temperature. This is NGC 6791. This is what I call the Lyra special branch cluster. What's odd about this is that it's on the list of globular clusters, but it's 8 billion years old. It has twice the amount of metals that we find in the sun. The dimmest stars are 6 billion years old, which are the white dwarfs, but there's another group of stars that are only 4 billion years old. And it's a strange hybrid between that. It's not like that of a globular cluster because the stars are not that old and they should have a lot more metals than what we find in a globular cluster. I mean, they have twice the metals that we find in the sun, but most globular clusters are not going to be more than 10% the amount of metal that we find in the sun. But yet it's not really an open cluster because it's just so old and has the gravity profile of a globular cluster. And it contains both the red and blue horizontal branch stars. The red horizontal branch stars, that's indicative of globular clusters because of their age. But open star clusters are younger, so they would have the blue horizontal branch stars. So we're finding stars that we find in both open and globular star clusters. So there's actually a few papers that were published saying this may be the discovery of a third class of star clusters. Neither open, neither globular, maybe some sort of a hybrid galactic supercluster or a galactic exotic cluster, because it contains the horizontal branch stars that we find both for open and globular star clusters. 1850, this is with the Large Magellanic Cloud. Right there, this is actually a combination of a double cluster and a superstar cluster. What's odd about this one here, which is the main body of stars, is a globular cluster. It has the appearance of a 50 million year old globular cluster just by the distribution of the stars and the orbital motions of the stars, because they can extrapolate theoretically just looking at globular clusters from galaxies that are hundreds of millions of light years away as what globular clusters would look like over many, many, many millions of years. But based on the spectra, the star, the globule, the cluster itself looks like it's only 100 million years old. So it's a very bizarre looking object. That right here is the subcluster. They found a subcluster of stars in the vicinity of this globular cluster. And it's a lot of massive young OB stars. And a lot of these stars rival that of the Pistol star, about 150 solar masses. This is Westerlong 1, one of a couple of clusters in the southern constellation of Ara. So it's an aura cluster, but you can see, look at the number of very rare high mass stars that exist. 1 luminous blue variable, 24 Wolf-Rayet stars. They have hypergiant stars. It has hypergiant stars, which is bizarre because globular clusters are not known for having any hypergiant stars. This is a very unusual supergiant star that has unusual amounts of beryllium in its spectrum. And it has several OB supergiant stars, all formed from a single burst of star formation. There is this interesting X-ray pulsar magnetar, which basically is a magnetar, a highly magnetic pulsar, about 100 trillion times the magnetic field of the Earth, but it releases all these anomalous X-rays. Based on studying that, the progenitor star, the star where it came from, would be about 40 times the mass of the sun.
Wait a minute, you say the pistol star was
No, the pistol star is not in that.
in the one.
You mean right here?
Yeah.
No, the pistol star is in another part. This is in the area of the Tarantula Nebula, but the pistol star is in another location. No, I said it was like the pistol star. Okay, one more object left. Messier 22. I couldn't get a right image for GJJC1. That's another nebula. I think this actually has 2 planetary nebulas, JGGC1 and 2. They're both infrared. They're almost impossible to see. But there have been some reports of seeing it with this one here at inverted vision. But you need over 900 power. You need an O3 filter. You need a 20-inch aperture. You need pristine dark skies. 2 black holes have been found at 10 and 20 solar masses. It's holding on to its black hole, so it's not very efficient in ejecting black holes. One thing about a lot of these globular clusters is that if they ever have any black holes, they literally get shot outwards along with all the other stars. So it's not just star evaporation rate, but it's also black hole evaporation rate. But it has an unusual large concentration of stars, much denser, less than 1/10 of a light year from each other at the central core of Messier 22. So we find is that what astronomers find is that there's possibly a central black hole cluster right at the heart of Messier 22. How many members? The star motion is a bit bizarre in terms of the kinematics, that is the mechanical behavior, but no less than 5 and no more than 100 members. So if you're looking for anywhere to find black hole clusters of black holes, not just star clusters, but black hole clusters, the greatest candidate to find black hole clusters is going to be looking inside the heart of globular clusters. And yes, they do have an evaporation rate for black holes, possibly along with the other stars. So that's a poet from Harley White who always liked to talk about poems in terms of the deep sky and having a lot of fantasy dreams about the stars at night. So yet may I phantom this vision deep, ere my life is rounded with a sleep. So when he looks at the deep vision of the night sky, it gives him a comfortable sleep with starry dreams. So that's it. That's my talk, my adventure into learning more about globular clusters and the weirdness of how many globular clusters have very bizarre features. Yeah.
That was awesome, Justin.
White dwarfs, why do they migrate to the center?
I think because a lot of those white dwarfs were formed from those big supergiants in the first generation. The combined gravity, they mutually come together, and when they blow apart, they have those sort of the dust and gas tend to form, let's say, the big giant stars, and then those giant stars, when they die off, they turn into those white dwarfs, and we find they're more migrated towards the center. But white dwarfs do tend to disperse outwards more and more towards the edge of the globular cluster. They tend to congregate more, and it has to do more with that mass segregation. Do we have the first generations of stars towards the center, and the second generations of stars being pushed out towards the edge?
Yeah, how are globulars doing for novas? We have a lot of them there.
For which?
For novas. Novas are super.
I've not seen any really indication of novas in these globular clusters. Mostly the novas and any nova activity would have occurred very early in the history of these clusters.
Some years ago, I heard that astronomers were using artificial intelligence to count and characterize craters on the moon.
Yes.
There's so darn many of them, right? When you said that the globulars typically have approximately 100,000 stars, is that because it's an estimate, or is somebody able to count them?
The old-fashioned method was to look at the outer, the middle, and the central region, pick like several areas, count the stars, and then extrapolate, take into account the size. With artificial intelligence, yes, you could probably go all the way out to where you have the half-life radius, where you have most of the stars, and then have AI just count all the individual stars from all the images.
The AI's had nothing else to do, so.
Well, it's not like they would count all, well, AI, yes, AI would do that. Astronomers would not have time to count all the other stars. So they developed formulas for extrapolating that.
Thank you.
Any other questions?
You know, build yourself a density function and integrate it.
Yeah.
Is there any process by which an open cluster could turn with time into a globular?
No. It's just all open star clusters are born in stellar nurseries. These globules were born when, as the galaxies began to form, lumps and chunks of the protogalactic cloud broke apart and rapidly collapsed on themselves to form these globulars.
There's a question in the chat.
Okay.
So the question is, from Wendy Walford, why don't they flatten out as they rotate around their center of gravity?
A few of them do flatten out, but most of them have sort of that uniformity of velocity. The others are fast on the edges and, slower around the edges and faster towards the center. But the variation of speed is just so small among those stars that there's no condition of them really flattening out very well. If they do flatten out, they would flatten out very, very slowly. But there are some globular clusters that do flatten out, but they're very, very few.
The question of the amount of gas clouds with the, that's what helps provide the friction, chew up the gas, chew up the momentum.
That would have occurred very early in the galactic formation. But beyond that, if they don't have any new generations of stars being formed, then the way the stars are distributed, it's not going to affect the orbital motions to where they will really flatten out. I did show one that was very unusually flattened. That would fit more like the very elliptical shape of the elliptical galaxies. Anybody have any other questions?
How globulars are actually formed? Massive star formation in a localized area, or these stars come together?
The general idea is that you get a protogalactic cloud. It's just mostly hydrogen and helium, just basic chemicals. And as it collapses in on itself, as it spins, what happens is that the material out in the end are loosely connected. And so they take a lot of that energy and they break off and they go into circular motion. And then as the material randomly breaks off in different bits along the edge of the protogalactic cloud, these huge lumps are then separated from each other. And then because they're very dense, along with the spinning, it adds a bit of torque that literally causes them to squeeze in on themselves. And then you get the rapid star formation that takes place. There's like that's the general theory right now. That could change as James Webb, as we look deeper into galaxies further away. I'm interested in how it looks like globular cluster formation, globular cluster evolution, because that idea may change, because as we're learning new things to change our theories of galactic evolution, the insight will be as how globular cluster evolution has changed in terms of theories of the evolution of globular clusters, because I think they play a huge role in giving us insight into the evolution of galaxies, because they're so old. They're sort of a timestamp of the distant past. Yes.
I gotta say, at the risk of showing my ignorance, I knew about globulars for decades, right? And I thought globulars were globulars, and they were all more or less the same. They were different from opens and other things, you know, the globulars are globulars. And now it sounds like there's hardly two of them that are alike.
That's right.
They're very different.
They'll have common characteristics, but there's enough difference between globular clusters that one will be a place where you can find planets and another place where you have just an unusual number of X-ray binaries.
Thank you.
And another one where it has more calcium lithium than what we would expect. Any other questions? Well, that's all, folks.
Just one comment from the peanut gallery. This is from Dave Roberts. He says, Justin, first class top drawer presentation, really outstanding, truly appreciate it.
Not bad in spite of some of the typos.